SwayamPrabha. Digital India. Educated India.
Hello everyone. So in this module, what we've been trying to do is we've been trying to look at turbulence as a random behavior, right? Although it is seemingly random to us. So that took us to looking at, say, the velocity recorded in an experiment, in a turbulent jet experiment, recorded at a specific point in space and time. And we realized that every time we repeated the experiment, we are getting a different value in velocity. It seemed to indicate that velocity behaves in a random manner. So it seems random to us, isn't it? So that took us to the point where we had to look at how random variables could be described. So we looked at some characterization of random variables. We understood the concept of cumulative distribution function, probability distribution function, which is basically the derivative of CDF, the cumulative distribution function. We looked at how statistics could be calculated, and later we looked at some examples of PDFs, right? Uniformly distributed variable, a variable that exhibits a gamma distribution, a log normal distribution, a discrete distribution. So like a Heaviside function as a probability, then the PDF as a delta function. So now, considering that we are dealing with fluid mechanics here, considering we are dealing with turbulent flows here, we are dealing with velocities. Velocities that have multiple components, velocities that are three-dimensional. So it is never going to be a single random variable, isn't it? It is going to be UVW. So we want to extend what we have learned so far to two or more random variables. That is what we are doing with joint random variables. Now, so let's have a velocity vector U. Let's call it U as a velocity vector, three components U1, U2, U3. Surely there will be a sample space which is also a vector, and the sample space components would be V1, V2, V3, isn't it? Now, if you have two or more random variables, then you will have a joint probability, a joint CDF, because U1 depends on U2 and U2 depends on U1 as well. So you would define a joint CDF as F12. So now you have the subscript represented by 1 and 2. And again, this is only for two components of, say, velocity. Okay, so here for now, just understand that we'll just deal with two variables for now, and we can obviously extend this to three variables. So the joint CDF would be defined by the probability of U1 less than V1, so that's one event, and U2 less than V2, so that's two events. So the joint CDF would be the probability of two events happening. So it is the probability of the sample point V1, V2 lying within the shaded area. Which shaded area? The one that is shown here. So this is the CDF. What is shown here in the right figure on the right is the CDF. So U1 less than V1 and U2 less than V2. Meaning, what is the probability that U1 is falling within this shaded area? What is the probability that this event is happening, and what is the probability that U2 is falling within the shaded area, as in U2 is less than V2. That is what the joint CDF is. So again, just like CDF of a single random variable, this also has certain rules that it follows, right? So F12 of V1 plus delta V1 and V2 plus delta V2 would be greater than F12 of V1, V2, indicating that it is non-decreasing. It is an increasing function. Just like a CDF of a single random variable is increasing, a joint CDF is also naturally going to be an increasing function. Keep in mind, one point I want to make here is the CDF is a function of the sample space variable. So f of v, u is the variable, is the random variable itself, whereas v is the sample space variable. So your CDF is a function of the sample space variable. So is your PDF. It's a function of the sample space variable. Now, this statement here means if I take a delta in the sample space variable in the one direction and in the two direction, it is going to be greater than the original CDF. That is what I've written here. And that's one way of writing that it is an increasing function. Another rule which you've already followed for a single random variable is that f12 of minus infinity comma 2, so comma v2, I'm sorry, f12 of minus infinity comma v2 is the probability of u1 being less than minus infinity and u2 being less than v2. Both of these should happen. That's a joint PDF. That's a joint probability. PDF would be a derivative. So that's a joint probability. So u1 being less than minus infinity, that is never going to happen, isn't it? So this is going to be 0. Not surprising. We saw this for a single random variable as well. Then I have f12 of infinity comma v2, meaning probability of u1 being less than infinity and u2 being less than v2. Here this is going to be the probability of u2 less than v2. Why? Because this is always going to be true. You're always going to have a velocity that is u2 velocity that is less than u1 velocity that is less than infinity, which means this is going to just boil down to the probability of u2 less than v2, the second event, because the first event is a certainty. So that becomes a single CDF, a single probability, also called a marginal CDF. The CDF f2 of v2 of the single random variable u2 is called a marginal CDF. The marginal CDF comes into play only when you have joint random variables. Only when you have joint random variables. Earlier we were looking at a single random variable. We don't call it a marginal CDF. We call it a marginal CDF only in the case of joint random variables when you take the probability of an event of one or the other variable separately. That is a that is a marginal PDF. Similarly, the marginal CDF of u1 is f1 of v1 equals f12 of v1 comma infinity, meaning the probability of u2 being less than infinity, isn't it? That is what this is. That is the second part. That's the second event. The first event is, of course, probability of u1 being less than v1. So just to be clear, so that we avoid any confusion here, this is in fact probability of u1 less than v1 comma u2 less than infinity. I hope this is clear now. So we talked about this shaded area, which is basically the probability of u1 being in that shaded area, u2 being in that shaded area, meaning u1 less than v1 and u2 less than v2. So this is a v1 v2 sample space showing the region of this event. Now on the left hand side, I have shown here a scatters plot of the v1 v2 sample space. So this is the actual event. So here in this particular scenario, u1 and u2 are joint normal, as in they are normally distributed. We saw examples of different random variables earlier: gamma distribution, log normal distribution, uniform distribution, normal distribution like a Gaussian. So in this case, u1 and u2 are joint normal with the mean of u1 being equal to 2, mean of u2 being equal to 1, the variance of u1 is 1, the variance of u2 is 5 over 16, and rho 1 2, which is a correlation coefficient, which I'll discuss in this class. Rho 1 2 is 1 over root 5. So for now, just understand that when U1 is a particular value, say this one, then U2 is this one here. So if U1 is close to, say, this is around 0.5, so this value is, for example, something like 0.4 comma 0.2, negative 0.2. So that's an example. So that U1, U2 space, that particular data point is 0.4 comma negative 0.2. So you have all these points that are there, and this, the probability of this sample, this distribution is what is plotted. Okay, and as an example, we have provided here a joint normal distribution. I hope this is clear. So we talked about the joint probability. Now let's move on to joint PDF. So just like we saw for a single random variable, the PDF is the derivative of the CDF, is the derivative of the probability, So now you will have a joint PDF, JPDF, and that is denoted by this lowercase f. You still have the subscript 1, 2 indicating that it is a joint PDF and it is a function of V1 and V2, which is now a double derivative because you have two variables. And this double derivative with respect to the sample space of F12, this is the CDF, isn't it? It is the joint CDF, JCDF. So this means that the CDF is the integral of the PDF, isn't it? Because the PDF is the differential of the CDF. The PDF is going to be, the CDF is going to be, the probability itself is going to be the double integral of the PDF itself. Now, here, just like for a single random variable, the PDF will follow certain rules. One is the normalization condition as shown here. So the double integral of the entire PDF over the entire sample space would be equal to 1. F12 of V1, V2 is always going to be a positive value because you are taking a derivative of an increasing function, which means it is always going to be positive. Another thing is, this only comes in joint random variables where you have F12 of V1, V2, and if you integrate it with respect to one sample space variable, so you integrate it with respect to dV1, you get your F2, V2, which would be a marginal PDF. So just like you had marginal CDF, now you have a marginal PDF. I hope this is clear. Now if you take any variable, okay, which is Q of U1, U2, and let's say it is a function of the random variables U1 and U2, then the mean of that variable can be obtained by integrating its product with the PDF. Just like we saw earlier, if you wanted to take a mean, you integrate the product of that variable and its PDF together over the entire sample space. So that is what is shown here, right? So this is the mean is equal to Q of U1, U2 times F12 of V1, V2. This is not equal to 1, so that wouldn't be the case, but this is actually the average. Now this means U1 and U2, the means and the variances can be determined from this equation or equally from the marginal PDFs, isn't it? So we can determine the means and the variances from the PDFs as well. Here, this is showing the probability of the event. So this is a V1, V2 sample space showing the region corresponding to the event. So here V1A is less than U1, less than V1B, and V2A is less than U2, less than V2B. So what we are saying here is, what is the probability of U1 falling within a region and U2 falling within a region? So that takes us to the correlation coefficient. Now, since we are having two random variables, right? We took an example where we have more than one random variable. We took the example where there were two random variables. So there is a correlation between the two variables, and we will have to look at, and that is quantified through something like a covariance. So covariance, so just like we have variance for a single variable, now we have a covariance for two random variables. So cov is how I'm going to call it. Covariance of u1, u2 is basically the variance of, or the mean of, u1, u2. This is the fluctuation, by the way. It is u1 minus u mean, isn't it? u1 small, lowercase u1 is equal to u1 minus mean. And same way u2 is equal to u2 minus mean. Okay, so that the lowercase represents that. It represents the fluctuation. Now, if you want to find out the covariance, it is v1 minus u1, v1 minus u1 mean, and v2 minus u2 mean multiplied together, multiplied with the joint PDF, which is f12, v1, v2, dv1, dv2. And if you want to consider a normalized value of that, you can consider the correlation coefficient, which is rho 12. The definition of rho 12 is u1, u2 mean. This is like a covariance divided by the variance of each variable. You see how we are doing it. And since the variance is squared, we are taking a square root. So you have u1, u2 mean, which is a covariance, and then divided by the variance of each variable separately. So u1 squared times u2 squared, and because both of those are multiplied together, we are taking a half so that it becomes non-dimensional, so to speak. So this is a correlation coefficient. It's basically a normalized value of the covariance. Now, this rho 12 physically means something. If it is greater than 0, that means they are positively correlated. What does that mean? u1 greater than 0 values are associated with u2 greater than 0 values. They're positively correlated. If rho 12 is less than 0, then they are negatively correlated. What does that mean? That means u1 greater than 0 values are associated with u2 less than 0 values. And because this is a normalized quantity, I'm talking the correlation coefficient, because this is a normalized quantity, rho 12 is going to be between -1 and 1, and you can see that easily from this equation. Now, what happens if it is equal to 0? Means u1 and u2 are uncorrelated, and if it is equal to 1, they are perfectly correlated. So 0 means uncorrelated, equal to 1 means perfectly correlated. If this is equal to -1, that means they are perfectly uncorrelated. So you have positive correlation and negative correlation is there. Then you have uncorrelated, then rho 12 is equal to 0. Perfectly correlated means equal to 1, and perfectly uncorrelated means it's equal to -1. So if you consider samples with u1 approximately equal to v1a and those with approximately u1 equal to approximately equal to v1b, they are likely to have significantly different values for u2. So we can look at conditional PDFs then. So that is illustrated through this figure. So on the left hand side, I have a scatter plot of u1, u2, and if you see here, this is a negatively correlated random variable. This is an example where I am considering negatively correlated random variables u1 and u2. And if you notice, I have the scatter plot where most of the points are in the negative v2 direction, indicating that most of the points are here. That too, they are biased towards the lower half of the plot, indicating that as u1 is positive, u2 is negative, highly negative. So clearly, at least visually, we can say that this is probably negatively correlated. And it does say that it is negatively correlated, that's one thing. And also, if you look at the correlation coefficient, rho 12 is negative square root of 2 over 3, indicating that they are negatively correlated. So visually also it seems like that, isn't it? But you cannot be sure until you actually quantify it. Visually also it seems that most of the points are in the positive V1 space, whereas the negative V2 space, indicating that they are negatively correlated. Okay, so that's one thing. Then the mean of U1 is 1, the mean of U2 is negative 1, variance of U1 is 2, and variance of U2 is 12. Be that as it is. Now, what I want to do is consider a conditional PDF, meaning you see this dashed line drawn here. So I want to consider all the points such that V1A is equal to 1. Meaning, what I'm trying to say is, what is the probability of all the points in this range? What is the probability of all the points in that range? Meaning, if when V1 or when U1, I should say, is equal to 1, when U1 is equal to 1, what is the probability of V2? What is the probability of V2 here? When V1 is equal to 5, what is the probability of V2? That is what is drawn here. So on the right side, I have a joint PDF of the distribution, and I will see, you can see that this is the probability distribution function, right? Probability distribution function. So this is a joint PDF of when V1 is equal to 1, meaning it's a conditional PDF. So for V1 equals 1, what is the joint PDF? So it becomes a conditional PDF. Same goes here. For V1 equals 5, what is the joint PDF? That becomes a conditional PDF. So these are all the points when V1 is approximately equal to 5. The PDF of all the points when V1 is equal to 5. So clearly you can see that these curves are shifting towards the left, meaning shifting towards the negative of V2, and that is indicated by the scatter plot as V1 is increasing. As V1 is increasing, my V2 is going more and more negative, and that is what is indicated by this arrow here and this arrow here. Isn't it? So I hope that was clear. So that is the conditional PDF. The conditional PDF is non-negative and satisfies the normalization condition. Just like any other PDF, it satisfies the normalization condition. For a given V1, if F1 of V1 is 0, then F2 of V2 conditioned on V1. So the bar here indicates that it is conditioned on V1, meaning for a fixed value of V1, what is the joint PDF? And if this V1 is 0, F1 V1 is 0, then you cannot define the conditional PDF. So just like you have conditional PDF, you have obviously conditional mean as well. So the conditional mean of Q, U1, U2 conditioned on U1 equals V1 is that variable multiplied by the conditional PDF. So Q of V1, V2 times F21, V2 conditioned on V1 integrated with respect to V2. Now these, you might ask, where do we use this, right? These are actually used in especially chemical reactions and combustion calculations where we want to find out, say for example, the temperature at certain locations where the mixture fraction is a certain value. Let's say you have a turbulent jet flame. The flame exists where the mixture fraction has certain values. So you want to find out, say, the temperature on the flame, in which case what you would do is you would find out the conditional PDF of the temperature conditioned on the fact that the mixture fraction is a particular value, say 0.5, say 0.4 or 0.6, depending on how the stoichiometry of the reaction is. So that's an example, an application of conditional PDF. Another point is, if U1 and U2 are independent, then knowledge of value of either one of them provides no information about the other if they are independent. Consequently, conditioning has no effect and the conditional marginal PDFs are the same if they are completely independent of each other. So F21 of V2 conditioned on V1 is equal to F2 of V2, and also F12 of V1 V2 is just F1 of V1 times F2 of V2. This is if U1 and U2 are independent. If they are independent of each other, then you cannot have a joint PDF, then they are just separate marginal PDFs. So the marginal and the conditional PDFs are the same. So again, this is something that we have covered in terms of marginal PDFs, conditional PDFs, joint PDFs. So we started with talking about joint random variables in this class. We looked at joint probability, joint PDF. So, and we looked at the rules of joint PDFs. They would be the same as what you had for a single variable. Then we looked at conditional PDFs and including the marginal PDFs as well. So that completes what we wanted to talk about PDFs. And now we are going to deal into more concepts that are related to the turbulent flow aspect. So we're going to look at random process paths. We're going to look at correlation coefficients, autocorrelations, integral time scale, and then furthermore we are going to look at frequency spectrum and so on. Thank you.